this module is supposed to demonstrate how to interface a analog sensor to an ADC and acquire that data. Okay. For that purpose we have taken an air quality sensor, and that sensor interface we will try to make it and show you with respect to a physical demonstration, which means that you are that means this sensor has to be connected to the analog pin of either an SOC or to that of a standalone ADC that is available. Okay. Now if you have to if you identify a board, let us say a board like let us say an aggregation board like Raspberry Pi or any one of those multi-core single board computer based systems, usually such boards will not have analog inputs. That is a problem because it has a different purpose. So you can't think about that as a unit for sensing. It is mostly for aggregating data from several embedded systems and then giving the data over a digital bus to this aggregation unit. So the purpose is different, and it is a high compute because it can run an OS, then it is multi-core, it can connect to the internet, it can transfer data. As it is receiving data from the digital ports, it can also upload data and so on. So it is a very powerful single board computer, particularly if you look at Raspberry Pi and those kind of class of single board computers. If you now decide that I will interface a ADC to this Raspberry Pi, you have left no choice except to look for an isolated one single ADC chip, and which gives you digital output so that you can interface it to the Raspberry Pi. On the other side it should be able to give you analog input. So just to sketch this picture, we will have you want to connect analog inputs on this side, you want to generate ADC conversion here, and then you want to transfer this digital data, to a single board computer such as Raspberry Pi. Okay. So these are digital ports. Typically this digital data and this digital port can either be over a 2-wire interface or it can be over a 3-wire interface, sometimes even a 4-wire interface. Okay. It can be 2-wire, 3-wire or 4-wire. If it is 2-wire interface, okay, actually this arrow is in both directions, so we should not restrict ourselves to one direction only. In fact we can show it here, we can show it here and so on. If it is 2-wire, these kind of systems typically have what are known as pull up resistors. This is a digital bus, right, and this digital bus has a name called I2C, inter IC communication, inter IC communication, that is why it is called I2C. Sometimes you may want to do it over 3 or 4 wire, in which case you will still have these 2 lines, plus you will have an additional 3rd line which could be unidirectional, and then there will be a another line. Okay. This kind of is also another way of transferring data, and this is also a digital communication between ICs, and such an interface is called SPI, okay, serial peripheral interface, and the other one as I mentioned was I2C, which is just 2-wire, and this can be SPI can be sometimes 3 wire and sometimes also 4 wire interfaces. Of course, this will give you much higher data transfer speed. Is much higher as compared to I2C and so on. It has its own advantages. Why two different types of digital interfaces? Because each one has its own advantage, okay, and one of them is indeed high data rate. If you want, you have to go in for SPI kind of interfaces. Okay. Now let us take, that was not our objective. Our objective was to connect a analog ADC chip to a single board computer such as a Raspberry Pi. We drew this picture and let us redraw it again by removing all the clutter that we had, and essentially just look at some plain stuff. Okay. Okay. So here you are getting digital. One such chip that is quite popular in the IoT world is this chip called MCP 3208. Okay. Now if you open a data sheet like this, what you will be sort of alarmed is to see these features, okay, and you must know these features in some detail, particularly in this course, and understanding the data sheet becomes a very critical part. Let me first give you a high level view of these parameters, and then we will do a demonstration and then get into further details of these parameters. Okay. First of all, the resolution of this ADC is 12 bit. That means every time it samples an analog value, it converts it into 12 bits. That is the idea of being a 12 bit resolution ADC. Then this ADC, any sampling operation, any analog signal sampling operation cannot be noise free, cannot be without non-linearities in the sampling process. Any ADC is characterized by the non-linearities associated with that chip. You have no way but to escape from that. So first of all, you should get an idea what are all the non-linearities and how did the manufacturer or the vendor quantify those non-linearities. First thing that occurs to you is, after 12 bit resolution, the second parameter he shows is DNL. Okay. DNL essentially stands for differential non-linearity. Okay. The DNL parameter is plus minus 1 LSB maximum. Okay. How did you arrive at this plus minus 1 LSB? We will come to that separately. Similarly, there is something called INL, which is integral non-linearity, that is also given as plus minus 1 LSB INL. Okay. And MCP 3208 and MCP 3204, there is no difference except that 3208 gives you 8 analog inputs. You can interface up to 8 analog inputs, and the chip provides an on chip sample and hold, because you have to sample the analog input and hold the output, so that the output is exactly for that sampled input. So you need another circuit called sample and hold, and that sample and hold is integrated inside it. If you are not clear, hold on for 2 minutes and I will explain how that thing works and how the overall architecture of an ADC actually looks like. Then we said that the analog inputs can either be with respect to ground, an analog output from a sensor with respect to ground, or with respect to the difference between two outputs. Typically, if you configure it in a bridge, if you put a sensor output, you are trying to draw sensor output from a bridge circuit, you will get differential output. There is no ground there. It is the difference between V1 and V2 that you are taking in and then converting that. Okay. So, you will get two voltages essentially, but if you are measuring, if you are getting a sensor output with respect to output voltage and ground, then it is called single ended, otherwise it is differential. So, you will use differential. Why you have to use differential? Sometimes why does someone want to use differential? The simple reason that any noise that appears in one line will also appear on the other line, and therefore when you feed it to any amplifying circuit, the noise from both of them get cancelled out and you will only get a clean signal. That is why you need differential inputs. In fact, several digital buses actually provide you only differential signals, and this is a very important requirement, because noise, if you have a single ended one, noise is very simple, easy to get injected into that line, okay, because it is with respect to ground. Any small lift from the ground is a voltage, and that voltage will interfere with the sensor and the sensor's output, and then that sensor output will be swinging with respect to the actual output that has come. So, that can create a sort of an issue where you are not able to digitize that value properly. So, with single ended, I mean with differential, you will avoid that problem anyway. So, that is one thing. And then I mentioned about sample and hold. I also mentioned about the SPI interface, so I will not go into the details, though this chip supports that. This chip also says that you provide me a range over a operating voltage range anywhere from 2.7 to 5.5, and people actually use 5 volts sometimes, and also people use 3.3 and so on. Next parameter is 100 kilo samples max sampling rate at VDD is equal to 5 volt, and it is down to 50 kSPS, kilo samples per second max, if the VDD is operating at a lower voltage of 2.7 volts. So, directly related to the sampling frequency, the sampling rate is or sampling frequency is directly dependent on the operating voltage here. Now, let us eject out of this data sheet, otherwise you will be wondering why this sampling is a very important thing. Let us go back to this basic picture that we drew, and I will explain a little bit about the sampling itself. If you take 10 kilohertz signal, if you take a 10 kilohertz signal, it boils down to 100 microseconds, right. You do 1 over 10 kilohertz, you will get 100 microseconds. Now, let us say an ADC specification provides 112 microseconds. Okay. That means if you convert this back, you will get, maybe I should just organize this slide a little better. I will take a new sheet and we will go to that. So, let us start here. You have a signal, an input signal which is coming on to the ADC at 10 kilohertz, which means it is 100 microseconds, period is 100 microseconds. The specifications that you have with you with respect to an ADC in your hand gives you 112 microseconds. Let us say you have 112 microseconds. If you convert this 112 microseconds, you will get back how much? Close to 10 kilohertz, but far away of course, because you get about 9 kilohertz. Now, if you want to sample a 10 kilohertz signal, if you want to sample successfully and apply the Nyquist criteria for a 10 kilohertz input signal, you need at least 20 kilohertz. Okay, you need at least 20 kilohertz. Now, by the way, people interchangeably use 20 kilohertz to 20 kilo samples per second, both mean one and the same. So, I will replace this with 20 kSPS. Now, it is easily connecting, right, because you saw the same number. 20 kSPS is something that you must minimum support if you are getting an input. This is your input to the ADC. So, let me draw this here. This is your 10 kilohertz signal, this is your ADC. It should sample the signal, let us say this is your analog signal, it should sample the signal at least 20 kilohertz, if not higher than that. Typically people choose, it is common to choose 100 kSPS, that means you are doing 10x. Why 10x? Because it is arriving at 10 kSPS, you are sampling at 100 kSPS. Okay. Now how to do this? That is the question. So commonly people choose, this is just a thumb, okay, they choose 10 times that, so it should be 100 kSPS. Okay. Now some SOCs and some ADCs will let you tune with what is known as a prescaler. Please look up, I do not want to diffuse, so I want you to look up the prescaler. Okay. This is something that you can configure on your ADCs. There is something called a prescaler value which you can try, and that will essentially change the sampling rate. Why I gave this example is Arduino typically does this 9 kilohertz sampling, okay, or 9 kSPS, and you do not get anything if you do a sampling at that 1x the input, you get nothing, and 2x is the minimum, that is what Nyquist sampling says, and yet that's also the very bare minimum that one can use. So people usually choose up to about 10x, which is quite common. So having got this much to understand, let us go back to the data sheet. So I will keep ejecting and coming back so that we connect everything about the data sheet. So now let us see this. The sampling kSPS maximum is 100 kSPS. That means a 10 kilohertz signal can beautifully get sampled, no problem at all. Okay, if you supply a 10 kilohertz signal, because you are sampling at 10x times more, that is possible, but that should be possible only if you operate the chip at 5 volts. Okay. Otherwise you can only do it at 5x the input frequency. I am making an assumption that the input is at 10 kilohertz, please note, that is why I am saying 5x, then it comes to 50 kSPS, and that is possible. You are putting it down to 5x because you are also operating it at a lower voltage. See, you have to be very careful about all these numbers, because why are you taking 10 kilohertz and giving you 5x at 2.7? If your signal is swinging at 10 kilohertz, I do not think you should ever compromise on working at 2.7. You should put it back to 5 volt and you should do 10x sampling only. This option you should choose 5 kSPS when your signal is at 1 kilohertz, not 10 kilohertz. Okay. That will help you to you get at least 50x, you will get something like close to 50x, which will allow you to sample. So it depends now on your input frequency, say analog signal frequency that is coming in, and accordingly you should choose that. This is one part of the story. Then let us come to the technology under which this chip was manufactured. So let me just expand this to a little bit so that you see these things much more clearly. Okay. So you see low power CMOS technology, 500 nanoamps, standby current is so much and active current is 400 microamps and all that. It appears to be good for good low power system, and it appears to be used in applications such as sensor interface and so on. That is also a very nice thing about it. Now we should know, I mentioned to you that I will explain a little bit about how this ADC works, and I could not find a better picture than what I found in this little diagram here. So let us spend some time. I drew that previously about mux, analog mux and so on, but I think the best capture is actually in this picture. So let us go through this picture. I will give you a high level view. Basically any analog signal will get fed here, okay. Channel 0 to channel 7 are your 8 analog inputs which come in here. The actual conversion is only on one channel at a time. Please note this, it is only one at a time, because the core of the electronics, which is all this system here, is just one block. For example, you have only one DAC, you have only one comparator, and you have one 12-bit SAR and so on. So these blocks are the heart of everything, and they essentially can only work on one signal at a time. So although you have channel 0 to channel 7 as inputs, you can connect 8 sensors. At a micro instant in time you basically can only sense one, and then you have to write your software logic to go to the next, to the next, the next and so on. So giving you a pseudo feeling that all 8 sensors are being sensed in a simultaneous manner. You will only get that pseudo sense, but you must note that there is a delay when you do round robin. For instance, channel 0, channel 1, channel 2, channel 3, you go up to channel 7 and then you come back to channel 0. That delay is what you will have to factor in when you have your signals coming in, okay. And that works very well when the signals are varying slowly or at a lower frequency. You will be able to satisfy this condition of moving from channel 0 to channel 7 and then coming back to channel 0 in time to catch up for the next wave that comes in. So all that will have to be factored in. Actually a successive approximation ADC, there are many types of ADC. There is something called flash ADC, there is a sigma delta ADC and so on. So many different types of ADCs are there. This is one type of ADC, very popular ADC, up to about 16 bits or so. If you take 4-bit ADC, 8-bit ADC, 12-bit ADC, 16-bit ADC and so on, they more or less use the successive approximation ADCs, and that is what is contained in these 3 blocks. DAC, comparator, 12 bits are the 3 heart of the whole system, and that is where the whole ADC actually works. It is strange that your ADC actually contains a DAC, that means it has a DAC, digital to analog converter. Why? Now we will understand why that actually happens. So when you have an input signal coming in on channel 0, that is being fed as an input to this comparator through this sample and hold. I mentioned to you that sample and hold is a very important block which will hold the output for that input signal, that is very important. So it will hold the output. So that signal is fed here. Now comparator is actually a device, a block which gives you 1 or a 0. It will not do anything more than giving you 1s or 0s. In fact your input signal is actually sensed whether it is 1 or a 0, actually it actually does not get converted in that sense. The actual conversion is actually happening based on what the 12-bit SAR feeds into the DAC. When the 12-bit SAR feeds into the DAC, okay, the DAC gives an output and then you get a comparator output which is 1 or a 0. Let me give you an example here. So let me go back. How this actually does is, this is your comparator, okay, this is your V in. Now you have to be careful, I will not put my V in directly, I will pass it through SNH here, I will just show it like this, okay. This one is actually coming from the DAC output, okay, that means it is giving you an analog output. Now what is the DAC output, why is it giving an analog signal? Because that is the business of the DAC. It is supposed to take a digital input and then gives you an analog output. How it starts is, it will first start with the, let us say you have a 4-bit ADC, it will first put 1 in the MSB 0 0 0 corresponding to this 1 in the MSB, some voltage is given, and then it will check whether this will give you a 1 or a 0. Okay. Now a comparison actually happens in this comparator. Based on the output of the comparator, you actually know whether this 1 should be retained or whether this 1 should be flipped, and you should try 0 1 0 0, or whether you should try, if it actually gives you a 1 output, you are happy, then you say I will try 1 1 0 0. Please note, okay, whether you are trying MSB 1, whether this, if this succeeded giving you a corresponding output, then you will try 1 1 0 0. Now if this failed, what you will do, this succeeded already. So what you will do, you will make 1, this failed, so I will make it 0, then I will make this bit 1, then this I will try. If I try like this and if this succeeded, fantastic. So I will retain this bit and this bit, now I will try this bit. Which one I will try? 1, this failed, I will leave that, this passed earlier, now I will try this. If this also passes, then this is the output, finished. So each time you will do a approximation, you will do a comparison, and then that comparison is essentially what is fed out. So you do one bit at a time, one MSB position at a time, and keep rotating it. So let us go back, and I hope you got this picture. If you indeed got that picture, let us go back and look at this one. Okay. So this is your comparator, and this comparator, this 12 bit SAR is actually giving you the digital value or the code word that is held, the digital value that is held, for which the comparator passes based on the MSB and the other corresponding bit positions. So with what will DAC give you an output? It will give you an output based on its reference to which it is fed. Vref here, when you talk about Vref in an ADC, actually it is being fed to the DAC block of the Vref. So your analog input is actually compared with that of the reference that is fed to the DAC, and that Vref actually will give you a corresponding analog. With respect to Vref, you will get a corresponding output from the analog output from the DAC. That is how your two analog signals will come. In other words, let me put back this picture if this is confusing. If this is Vref here, okay, I have to, yeah, let me shift it a little bit. If this is 5 volts, okay, if this is 5 volts, this will be what? 1 0 0 0. Try and tell me where exactly this 1 0 0 0 comes. This will be exactly at half, it will be exactly at half, correct. If you go above 0 0 0 0, 0 0 0 1, 1 0 and all that, and then 1 here is essentially exactly half. Half of 5 volts is how much? 2.5 volts. So if this pattern is sent, it is actually giving you how much here? 2.5 volts, that is all. And now you compare your input with respect to this 2.5 volts which is being fed, and then you come up with simple expression which is code word is equal to V in divided by Vref. So you see it is a ratio of V in by Vref into the 2 power n, where n is the resolution. This is the basic expression which everybody starts off when we talk about ADCs. So let us come back here. Let us come back here. So you see this functioning we now know very well. Beautifully we have understood how the ADC works. Still we have not yet figured out how do we interface this ADC, right. We just discussed a few things. Okay, this you can read, you can download this data sheet and you can read it. but we have not yet crossed over because there are some very crucial parameters which we have to understand before we move on. And what are those? Those come from this data sheet here, continuing on the data sheet. One of them is the conversion time. Okay. If you feed a clock to the ADC, you need 12 clock cycles to convert from analog to the digital domain. That is what the conversion time is. Then you have analog input sample time, throughput rate. We mentioned this already. Some people call it sampling frequency, some people call it throughput rate, and so on. It is nothing but that 100 kSPS at Vref of 5 volts and VDD of 2.7, we said it will come down to 50 kSPS. Then we said all the things about accuracy of the ADC, DC accuracy of the ADC. Look at what he has said. Resolution is 12 bits, that appears okay, great, we know about the resolution. But what about the other problems with respect to ADC and its linearity? Definitely it has an integral non-linearity, it is called INL, and that is quantified with a typical number of plus minus 0.75 LSB, and maximum it can go up to plus minus 1 LSB. And differential non-linearity is also quantified here. Offset error is plus minus 1.25 and the maximum it can go up to is plus minus 3 LSB. Gain error plus minus 1.25 plus minus 5 LSB. Then total harmonic distortion is this number minus 82 dB, which has a Vin of 0.1 volt to 4.9 volt at 1 kilohertz, and signal to noise and distortion is now down to 72, is at 72 for the same specification. So there are quite a few parameters which you have to understand because your choice of resolution actually has a bearing on this. You will, it is a very important parameter, at least you should know a few parameters, and I will give you some interesting insights into these things so that you will be able to read data sheets and understand them even better, okay, because this course is about choosing components. How do you choose these components? So unless you know these components, it becomes difficult for you to choose them for your projects, to choose them to make you understand this in a structured way. So our next task is to understand a few DC accuracy parameters, particularly offset error, gain error, and then we will just touch upon integral nonlinearity and differential nonlinearity. But before we do that, let us do a demo. Let us finish with a small demo so that this monotony of lecturing is stopped, and then we will come back and discuss these 4 DC accuracy parameters. You see this board has several sensors. This is an air quality sensor board. You will see that there is a sensor here, there is a sensor here and another sensor here, and there is one more sensor down below here. This is this here, sorry, this one. This is an interesting sensor. This is a sensor called SGX 4514. It is mounted directly on the board. It looks like a chip, and it is a NO2 nitrogen dioxide sensor and carbon monoxide sensor, both it will give, okay, and it is cross sensitive to other gases. So that is the idea, and it is a semiconductor sensor, gas sensor. These some of the sensors that you see here are actually electrochemical sensors, but the one that looks like a chip indeed is a semiconductor sensor. Now all these sensors are connected to a Raspberry Pi board which is connected on top of this, it just goes on top of this, okay. There is a box covering box, and on top of this box there is a board, and you can see the standard headers directly interface to the Raspberry Pi. But if you reverse this picture, reverse this board, you will see the whole lot of electronics here, okay. And what you see here, this one for instance, is indeed our famous ADC chip, and this ADC chip directly interfaces to the Raspberry Pi, and that is the nice thing about this chip, that this ADC chip can actually interface very well. This ADC chip can interface very well directly because it gives digital output, takes analog input and gives you a digital output, and over SPI interface it connects directly to the Raspberry Pi. Forget about all what you see here, this is all this using a glue gun to arrest some wires which we had to patch up. This is just a sample board that we were using. So what is the corresponding code software for this particular board? Well, let us look at that. That one essentially talks about acquisition of data, and how do you take that data and how do you acquire the data, and then how do you convert that data into corresponding analog input, right. You want to know what is the analog value that came in through your code. So you see now, if you look carefully, the MCP 32808 SPI is indicated, right, that is SPI. Code in the computer says that you read over SPI, you can see that A0 is equal to SPI dot read, you are saying. That means the digital value corresponding to that analog output is actually stored in A0, alright. Next what you do, you want to know what is the sensor voltage output, okay. So what do you do? Well, it was quite simple. What you do is, this essentially is, you are interested in the input voltage, which you can simply get from this expression here. This is code word divided by 2 power n times Vref, okay. That is essentially what we had shown in the code as well. So if you look carefully into the code part, the code part simply says A0, that is your code word, essentially the analog output, the digital output, divided by 2 power n, which is in our case it is a 12-bit ADC 4096 times the reference voltage, which is 5 volts. So you got back the analog input as seen at the input of the ADC. So this is how you acquire the data, and now once you know your input voltage, for that particular voltage what is the processing you will have to do, the data sheet of SGX would have told you. So you go there and do a few more manipulations, you will be able to read NO2 quite accurately. We will do that also, we will try and see what is the end of the chain of how you take this analog value that you painstakingly measured through the ADC and then got the digital output and then converted it back into the analog output form, and how can you use it effectively, and then we can process from there. We will do all of that, but before that I promise that I will go into a little more of detailing with respect to the ADCs and its performance, which we will take up in the next class. Thank you very much.